Hello again, this is Professor Roman. Welcome back to my lecture series entitled Transition to Advanced Mathematics. Let's take another look at the ZF axioms and how they might be used to define the natural numbers. What are the natural numbers? Most people just take them for granted, 0, 1, 2, 3, 4, fine, no problem. But a mathematician can't do that. Somebody representing mathematicians has to give a formal definition for natural numbers so that the rest of us mathematicians can use that concept of a natural number. Actually, there have been many definitions proposed for natural numbers. Our old friend Leopold Kronecker, who had some trouble with Cantor's theory of sets and with Dedekind's theory of order, he said, God made the integers, all else is the work of man. That's not a very constructive or useful thought. We need something more constructive, more useful. The most natural definition of the natural numbers is the following. To define the natural numbers, you've got to construct them out of the only building blocks that we have, which is sets. Moreover, according to the ZF axioms, we initially have only two sets, the empty set and an infinite set. The infinite set is not really a good candidate for defining a natural number, even 0. So 0, that only leaves the empty set. No problem. We will define the natural number 0 to be the empty set. And when I say we, I'm saying the mathematical community defines 0 to be the empty set. This is the symbol for the empty set, and unfortunately, it looks a lot like a 0 with a line through it, but it's not supposed to. It's not a 0 with a line through it. It's a circle with a line through it, and it's inspired by a letter from the Danish and the Norwegian alphabets, just so you know. Well, so we have defined 0 to be the empty set because we only have two choices. 0 has to be the empty set or an infinite set, and we don't want it to be an infinite set. What about the natural number 1? It's got to be a set. Again, the infinite set is not a good candidate, but the empty set is now taken. However, the empty set as a set is available to be an element of another set. In fact, the axiom of pairs, where the two sets that I called S and T when I described the axiom, they could be the same, and they could be the empty set, in other words, 0. And if we apply the axiom of pairs to this situation, we get another set, and it only has one element. It's not really a pair because S and T were equal. It's the set containing 0. So in other words, the axiom of pairs tells us that this is a legitimate set. Remember Russell's paradox. We have to be careful what we claim to be a set. But this follows from the ZF axioms. So we'll define 1 to be the set containing 0, or the set containing the empty set. What about 2? Well, we've already got a pattern. 2 will be defined to be the set containing 0 and 1, which is permitted because it is the union of the set containing 0 and the set containing 1. So we use the axiom of pairs and the axiom of union, and we know that this set exists. In general, we can define the natural number n to be the set containing all the natural numbers we've previously defined, 0 through n minus 1. So to get the natural number n, we collect all of the natural numbers that have been defined so far and throw them in a set. That's n. And the ZF axioms permit us to do precisely that. Once the natural numbers are defined, as we have done thus far, we can define other sets of numbers, such as the integers. That's easy to do. The rational numbers, not too difficult to do. And the real numbers, tricky. That one is difficult. That's a proper definition of the real numbers may or may not appear in an upper division course in real analysis. It will certainly appear in a graduate course. Well, we've defined the natural numbers then. And those are the numbers 0, 1, 2, 3, and so on, formed in the way we described. Unfortunately, there's a little bit of controversy. It's minor, but it's annoying. Some people define the natural numbers to be this set, starting at 1, 2, 3, omitting 0. I've seen this in numerous books. In fact, even in Math 13, even in this transition class, I was using a textbook prior to the one I have written here, and the authors said the natural numbers start with 1. I find that personally annoying. But it seems to be, and I haven't done a comprehensive survey, but it seems to me when you look in lower level books, for example, high school algebra, or even slightly higher levels, in fact, as I say, some books even on the subject of transition to advanced math, you'll find that the natural numbers are often defined starting at 1 rather than 0. But for reasons that should now be rather obvious, most mathematicians define the natural numbers as including 0. That's where they all came from, the empty set. It would not look good to have said, let's start with 1 as a natural number and we'll define it to be the empty set. That's sort of unpleasant. So it's natural that if you're going to do this from the foundations of mathematics, you would start with 0, and that would be defined as the empty set. But one of the upshots of this, of course, is that every time you pick up a book, at least at the lower levels, you need to double check what the author intends to mean by the natural numbers, As we have seen, the repercussions associated with Russell's paradox and other paradoxes motivated mathematicians, in particular Zermelo and Frankel, to take a more formal axiomatic approach to the foundations of mathematics. They developed their ZF axioms. But that wasn't the only sort of shock. The Russell's paradox wasn't the only shock that occurred around this time in mathematics. there was another rather serious crisis, you might say. And this centered around the seemingly innocent question, given a non-empty family of non-empty sets, a bunch of non-empty sets, can we choose one element from each set in the family to form a new set? I didn't say one distinct element. You can, if the sets overlap, you can pick an element from their intersection. All I care about is you get one element from each set. Well, this turns out to be a surprisingly complex question. The statement that it's always possible to make such a choice for any non-empty family of non-empty sets is called the Axiom of Choice, and it's often abbreviated AC. It was first formulated by Zermelo in 1904. Now, the term axiom is not really appropriate in this context because axiom means accepted without proof, and we're not saying that that is the case, not at this moment, but it is called the axiom of choice. I can't change that. If a family contained only a finite number, 12 or a billion non-empty sets, no one would be concerned about saying that you can pick an element from each member of the family and make another set. That would be referred to as the axiom of finite choice, and there's no controversy there. But mathematicians initially believed in the early 1900s that the axiom of choice should somehow follow. It seems so reasonable that it should somehow follow from the other ZF axioms. We should be able to prove it. But no one was quite sure how. However, a series of increasingly sophisticated techniques, beginning with the work of Frankel in 1922 and ending with the work of a mathematician named Paul Cohen in 1963, showed that the axiom of choice is independent of the ZF axioms, meaning that it cannot be proven. The axiom of choice cannot be proven from the ZF axioms. There cannot be a proof. And that came as quite a shock to the mathematical community. And it provides another example of where intuition failed many smart people. But the real shock came in 1938 when Kurt Gödel, probably the most famous logician of all time, and a close friend of Albert Einstein, by the way, showed that the axiom of choice is consistent with the ZF axioms, meaning that AC cannot be disproved either. So the axiom of choice is neither provable nor disprovable from the axioms of ZF set theory. Therefore, we call it undecidable. What to do? Well, every mathematician has to make a choice, if you will, as to whether to accept the axiom of choice as a legitimate new axiom or to reject it, or to remain neutral. Those who wish to accept the axiom of choice as valid have to then add it to their axiom system. And when you do that, you have what is referred to as ZFC. And you will hear mathematicians say ZF with choice. Okay. If you prefer to reject the axiom of choice, however, you do so at considerable significant cost, because a great deal of modern mathematics depends on the acceptance of the axiom of choice as an actual axiom. In other words, it's truth. For example, if you've studied linear algebra, this might make sense. The statement that every non-trivial vector space has a basis is equivalent to the axiom of choice. So if you reject the axiom of choice, you have to reject the statement that every non-trivial vector space has a basis. Well, these days, most mathematicians, by far the majority, accept the axiom of choice and so work within the structure of ZFC. But the Banach-Tarski paradox that we discussed earlier is a consequence of the axiom of choice. You need the axiom of choice to prove the Banach-Tarski paradox. So if you really absolutely refuse to accept or believe in the Banach-Tarski paradox, you have to reject the axiom of choice and thereby lose a great deal of modern mathematics. The choice is yours. But if you reject the axiom of choice, you'll be in the vast minority of people, of mathematicians. The axiom of choice did not provide the only surprises for mathematicians that were seeking to place mathematics on a solid logical foundation. The work of Georg Cantor, that I mentioned earlier, contained yet another surprise for mathematicians. And it concerned the relative sizes of infinite sets. So before examining Cantor's ideas very briefly, we'll do so in more detail later in the course, it is interesting to note that Cantor's work on set theory, and in particular on the notion of infinite sizes, sparked some very severe criticism at the time. Some Christian theologians accused Cantor of creating a challenge to the uniqueness of the absolute infinity in the nature of God, whatever that means. But more seriously, some very famous mathematicians, such as, again, Leopold Kronecker and Henri Poincaré, also found Cantor's work to be rather objectionable. Kronecker described Cantor in public, as a scientific charlatan, a renegade, and, believe it or not, a corrupter of youth. The philosopher Ludwig Wittgenstein lamented that mathematics, this is a quote, mathematics is ridden through and through with the pernicious idioms of set theory, which he dismissed as utter nonsense that is laughable and wrong. So, let's take a quick look at Cantor's ideas about the sizes of infinite sets. And we will return to this subject in earnest later in the book. And if you're young, if you're under a certain age, you might want to stop the video, avert your eyes, lest you be permanently corrupted. Consider the set, again, of natural numbers and the set of even natural numbers. If you ask a layperson, is the set n larger than the set E, I think you would probably get a lot of affirmative answers. After all, every member of E is a member of N. E is a subset, in fact, a proper subset of N, and there's a lot of extra elements in N that are not in E, all the odd integers. So from that perspective, it would appear that N is larger than E. That sounds very plausible, but it's wrong. From a strictly mathematical point of view, it's wrong. Well, before I can justify that statement, what we need is to carefully define our terms. What does it mean to say that two sets have the same size? According to Cantor, and accepted today by all mathematicians, two sets A and B have the same size if there's a 1-to-1 correspondence between the elements of the two sets. What does that mean? Well, a little typo there. If you have two sets, let's say they're finite, A1 through AN and B1 through BN, these have the same size because there's a 1-to-1 correspondence between the two sets. And that means that every element in one set, A, capital A, let's say, appears exactly once on this side. Every element of the other set appears exactly once on the other side. So it's what you might call a matching, a perfect matching of the elements of the two sets. And more formally, a 1-to-1 correspondence is a function from the set A to the set B that's both 1-to-1 and onto. Concepts you would have learned in calculus if you took calculus, and concepts we'll discuss at the appropriate time. So these two sets, for example, have the same size. Here's a 1-to-1 correspondence, and there are other 1-to-1 correspondences. Here is a 1-to-1 correspondence between the natural numbers and the even natural numbers. 0 corresponds to 0, 1 corresponds to 2, 2 corresponds to 4. Well, we can't finish this 1-to-1 correspondence. We need a formula, we need the function, and it is simply multiply by 2. That will send the natural numbers to the even natural numbers in a 1-to-1 and onto fashion. It's a perfect matching of the two sets. Therefore, according to Cantor's definition, which is now well established, the two sets have the same size. Any set that has size equal to that of the natural numbers is said to be countably infinite. And we will see later on when we discuss these matters in more detail that the integers are also countably infinite. The sets E, N, and Z all have the same size. As strange as that may sound. Even the rational numbers are countably infinite. If you're having trouble with this, then you need to think in the following terms. we have set down a definition. Everybody in the mathematical community accepts it. If you're going to join the community, you need to accept it. Unless you can figure out some logical argument that would change people's minds, but it's very unlikely. Therefore, you must accept the consequences of the definition, whether you like them or not. One consequence is that Q, Z, N, and E all have the same size. Maybe now you can begin to see why Kronecker and some others were very upset, even nasty about all of this. It appeared to many mathematicians prior to Cantor's revelations that all non-finite sets should have the same size. But Cantor discovered, along with what we've talked about so far, the following facts about infinite sizes, and they have become more formally known as trans-finite cardinal numbers. And we'll explain that down the road, so don't worry about the term right now. While the sets E, N, Z, and Q all have the same size, they're all countably infinite, the set R of real numbers is actually larger than any of these sets. Cantor showed, and we will do so, that there cannot be a one-to-one correspondence between R and the natural numbers. Cantor also discovered that the natural numbers have the smallest infinite size. So also would be the even natural numbers, the integers and the rationals. That size is the smallest infinite size. Cantor also discovered that for any infinite size, there's always a set with a bigger size. In fact, the power set of a set is always bigger than the set. So if we take a set, we form the power set and the power set of the power set and so on, we get bigger and bigger sizes of infinity. This raised an interesting question. If we start with the smallest infinite size, represented by the natural numbers, and we form this sequence of power sets, we get increasingly bigger and bigger infinite sizes, infinite cardinal numbers. Do we get all the infinite sizes? Might there be an infinite size in between these two, the size of the natural numbers and the size of the power set of the natural numbers? The statement that there is no other infinite size in between these two is called the Continuum Hypothesis. And we'll talk more about that terminology later too. The statement that there are no other infinite sizes in between any of these is called the Generalized Continuum Hypothesis, abbreviated GCH. So the question is GCH true or false? Well, it turns out that just like the axiom of choice, GCH is neither provable nor disprovable using the axioms of ZFC, even if we throw in the axiom of choice. So GCH has the same independent but consistent status relative to ZFC as the axiom of choice had relative to ZF. But whereas it was important to make a decision, every mathematician to make a decision about the axiom of choice, accept or deny, the generalized continuum hypothesis is different because it's not really in the mainstream of mathematics. Most mathematicians function for their entire professional careers without ever having to make a decision. Shall I accept it or shall I reject it? And what are the consequences? In fact, I would guess most mathematicians never even think about it. Or they may have thought about it briefly and said, okay, it's undecidable, but I'm not going to worry about it because it doesn't affect, I do algebra, I do differential geometry, I do probability, I do number theory, I don't much care. It's not going to affect the mathematics I do. Okay, well, we've gone through quite a lot of material here, and there's just one more thing that I wanted to discuss with you before we buckle down and get down to the real work at hand, and that is some of the terminology that we use in mathematics. Some of this we've talked about already, but the concept of definition. A definition is a precise and unambiguous description of the meaning of a mathematical term. On a practical level, definitions are usually given in one of two formats. They may be set out formally, as I have done with this definition, by using the word definition and then giving the definition different font, different color, and whatever to set it out from the rest of the text. But definitions are also given by bold-facing a term. So as you probably remember this phrase, I think earlier, a sentence earlier in the book, as you probably know, a positive integer is prime if it has no positive factors other than 1 in itself. Notice that prime is bold-faced. That is telling you this is the definition of the word prime. There's no distinction between the two formats in the mathematical sense. It's just a matter of style. And both are used quite commonly to make definitions. A theorem is a mathematical statement that's proved using sound logical reasoning. It's the conclusion of a proof. However, some mathematicians reserve the term theorem for the most important results in whatever context they're working in. Don't worry too much about that. It's a subtle point, and what's important now or not important now may be important tomorrow, so I wouldn't worry too much about that. But I thought you may as well hear that. Here's an example of a proof, of a theorem. Theorem 1.1, if m and n are integers, exactly one of which is even, then m squared plus n squared can be written in the form 4k plus 1 for some integer k. Okay, some comments about this. First of all, just as an example, 3 and 8 are integers, exactly one of which is even. And so the statement of the theorem is that 3 squared plus 8 squared will have this form, 4k plus 1. And of course, it's easy to figure out what k is. It's 18. Okay. You may find this statement of a theorem somewhat boring. I warned you earlier that the theorems we have, the theorems we're going to discuss in this book that require proof, the reason we're discussing them is to look at proof techniques. Many of them are either taken out of context or not particularly inspiring. Okay. Notice that the theorems are generally numbered so that they can be referred to later in the exposition. So here I would say, according to theorem 1.1, so-and-so happens. Equations are also often numbered, and that's a very useful thing to keep in mind. You will want to do that yourself. You will want to number theorems you write, and you will want to number equations. A lemma is a mathematical result whose primary purpose is to help prove one or more theorems. When a proof of a theorem requires a step that is lengthy and that can be separated from the main body of the proof, and especially when that step can be used to help prove other theorems, then it is often separated out as a lemma and proven on its own before the main theorem or theorems to which it applies are stated and proved. Here's an example of a very famous lemma, but first we need a definition. Two integers a and b are relatively prime if they have no positive common factors other than 1. So this lemma is called Bezos Lemma. It's very famous and very useful. If a and b are relatively prime integers, then there exist integers x and y for which xa plus yb equals 1. So for example, 3 and 10 are relatively prime. And so Bezos' lemma says there are integers x and y for which 3x plus 10y equals 1. And you can figure that out in some examples here. Some lemmas have become so important with time that they deserve the status of a theorem, and Bezos' lemma is one that would fit that condition, I think. Except there's another result that's referred to as Bezos' theorem, so we can't change this one. There's even a result called Bezos' little theorem. Apparently Bezos was a very busy man, which is why they called him Busy Bezos. A corollary is a result whose proof is generally short and relies almost exclusively upon a previously proved theorem. So it's almost a direct consequence of a previous theorem. Here's an example. This is a corollary to theorem 1.1 that we discussed already. For any odd integer m, there's an integer j for which m squared equals 4j plus 1. All we have to do is, in theorem 1.1, take n equal to 2, and then m squared plus n squared has the form 4k plus 1 according to that theorem. N squared is now 4. Move it to the other side. And so m squared has this form 4j plus 1. So this is a 2-liner, 3-liner, but relies very heavily on the earlier theorem, and so it is a corollary to that theorem. A proposition, that term is sometimes used to denote a result that's maybe not quite as important as a theorem, but still has considerable independent significance. But I think this term's fallen out of use. I haven't seen it that often in modern books. A conjecture is a statement that is unproved, but is believed to be true, at least by the person who first states the conjecture. The Collat's conjecture, the Goldbach conjecture, the twin primes conjecture. It's examples of conjectures that are believed by some or many to be true but have not yet been proven. A claim is an assertion made by someone who intends to prove the claim in short order. So, for example, I could say, I claim that there are infinitely many prime numbers. Then I would say, almost in the same breath, and here is my proof. An axiom or postulate, we've already discussed statements that are accepted without proof. Well, I hope that this introductory chapter has stimulated your curiosity about mathematics, or at least given you some sense of what it is you are faced with if you're going to pursue the study of advanced mathematics. I would also add not to be concerned if this seems a bit overwhelming at this time. That's not unreasonable. We're going to start now with our study of logic, and we're going to step things down and go through things very slowly and carefully.